Okay, we are talking about chapter 6, I think. Bless you. So we started talking about energy here in chapter 6 and a couple of ways that we talk about energy. One way is the delta H value, which is the enthalpy. And it's sort of the heat of a reaction. And when we calculate a delta H value, or if you're sort of given a delta H value, if it is a negative value, that means that the reaction overall was exothermic, which means that heat and energy was released. If you calculate or given a delta H value that is positive, that is an endothermic reaction. And that means that heat and energy was absorbed. And there's a couple different ways you could calculate sort of the delta H for a reaction. Very common way is to take the delta H of your products minus the delta H of your reactants. And there you go. And in a reaction, when we have reactants that go to products, basically the products are our final sort of state and the reactants are our initial state. And taking sort of the difference of the energy involved in those guys will give you sort of the delta H of the reaction. It is, as we maybe talked about, what's sometimes referred to as a state function, which means it doesn't really matter how you get there. The two really important things is sort of where you start and where you finish. And that's sort of in a reaction. Products are always our final state and our reactants are obviously our initial state. There is actually in books delta H table where you can look up values for everybody that's in the reaction, and you can add up all the delta H values for the products. You also do need to multiply by the coefficient and subtract it from all the delta H values from the reactants, So, if you looked in this table and A was 20 kilojoules, B was 10 kilojoules, and C was 10 kilojoules as well. Why not? Actually, we'll do 30. And if we had a reaction of like 2A plus 2B goes to C, and we wanted to calculate the delta H for this reaction, we simply would go to this table and basically do the delta H is our products, which would be just the C, which is 30, minus our reactants, which on the reactant side, in my example here, we have A, and there's 2 of them. So we take 2 times 20. The 2 comes from the coefficient. So when you look it up in the value in the table, you need to multiply by the coefficient, plus 2, which again is the coefficient here for B, times the value of B that we would find in that table, which was, sorry, B is 10. My made up answer here. And if we did all that, for example, here in this made up one, we would take 30 minus basically 2 times 20 plus 2 times 10 gives us a minus 30 kilojoules. This would tell me that this reaction was exothermic as it has a negative number. Question? That's what you get when you do the math here. Yes. So that's the number that you get when you do the math. You take 30 minus the 2 times the 20 plus the 2 times the 10. So because we did get a negative number, again, this would tell us that it is exothermic in this case. So that's a really common way that you could calculate the delta H. What we kind of looked at a little bit in the chapter was another way that you could calculate delta H, which is based off of what is sometimes referred to as bond energy or bond enthalpy. And that has to do with, basically you could think about the energy change that occurs in a reaction based on how many bonds you break versus how many bonds that you make. So another one was to use the delta H, which is sometimes referred to as bond energy. This is also another sort of table value typically that you could look up things. So let's just say, for example, we had something like this plus this, makes like and if we had a table of like an A B single bond was 100 kilojoules to break, a carbon or CC double bond was 300 kilojoules, and a carbon as a CB, I guess, is 125 kilojoules. By the way, I'm just making these numbers up, obviously. And CA was, say, we'll go with 175 kilojoules. So if we were to do this based on bond energy, which is like a table like this where you would look it up, these type of values, basically what you would do is just basically take accounting of everything you got going on in that particular reaction. So pretty much everybody on this side, all those bonds would need to be broken. And as we talked about, when you break bonds, it is an endothermic process, which is a positive number. And when we make bonds on this side, that is an exothermic type process, which is a negative number. So really, in this case, if you wanted to calculate the delta H of this reaction based off of bond energy and breaking and making bonds, you basically just add up everything that you would be breaking and everything that you would be making. So why don't we start with that? And again, this made up example, see how we do here. So on the left-hand side, we pretty much need to break a bunch of bonds. We need to break in this first molecule here, 1 AB bond, 2, 3, and 4 AB single bonds need to be broken. And if I went to my made up table here, I see that that would be 4 times 100 kilojoules. Again, I need 100 kilojoules to break up each of those bonds. I also would need to break a CC double bond here. And that would be 1 times, again, the value that I would look up in the table, which would be 300 kilojoules. That is all the breaking I'm going to be doing there on the reactant side. And I could get a total here, which would be 400 plus 300 there, would be 700 kilojoules of energy. Again, this would be a positive number, right? Because I got to put it in there. It's endothermic to break all those bonds. Now on the product side, I'm going to be making some bonds. And if I look, I need to make a CB bond, 1, 2, 3, and 4 different CB bonds. I always want to say carbon there. 4 CB bonds, which again, I could go to the table and look it up. And that would be 4 times 125 kilojoules. That's the energy required to make all those bonds. And then I would be left with one last bond I need to make over here, which is 1 CA bond, which I could come here and find, which is 175 kilojoules. So if I did that, 4 times 125 plus 175 gives me 675 kilojoules. Since making bonds is exothermic, technically speaking, all these values we would find from the table should actually be negatives. And so should this guy, which would be negative because it should be released to allow those bonds to come together. Now, if I wanted the actual delta H for this reaction based on bond energy, I basically just need to add both of these numbers together. All the energy required to break the bonds, all the energy required to make the bonds, and that would give me 700 plus a negative 655, gives me a grand total of 25 kilojoules. In my made up example here, based on bond energy, this reaction would be endothermic or exothermic. It would be endothermic, as we did get a positive value here. If you ever go to one of these tables, it's really important to do two things. Make sure you obviously get the correct bond that you're looking for between the two elements, but you also want to make sure you get the correct type of bond. Is it a single bond, a double bond, or a triple bond? As the energy will be different for those things, as we talked about in bonding. Again, a triple bond takes more energy to break than a single bond, so there will be different values. So it's really important to make sure that you kind of look those things up. So sometimes people will calculate the delta H for a reaction based on bond energy. And again, it's just really sort of an accounting of everything energy-wise to break all the reactants and energy-wise to make all the products there. And really that energy difference is for the reaction. Again, the previous example here is one where we're basically taking all the enthalpy values for each of these guys individually and taking the difference between the products and the reactants. And really what each of these sort of correlate to is we saw, I think, some energy diagrams. And, you know, we have our reactants and our products. And it is really that difference in energy between where the products end and the reactants started as to how you calculate your delta H of the reaction. This is an exothermic diagram where the reactants are lower in, I'm sorry, endothermic, where the reactants are lower in energy than our products. So it takes some energy being put in there to get us up to the products. And that is different than the one we saw where we had something that looks like this, reactants and products. Again, the difference in the energy of those two things would be our delta H for this reaction. In this case, we actually have to sort of release energy to get ourselves down to the products in this case, which is why this is an exothermic sort of process. Questions on that stuff there? We got into at the very end there as well, I think, equilibrium at the very, very end. What we were talking about with equilibrium is the idea of a certain type of reaction, which are reversible reactions. So if you had 2A plus B goes to 2C. Reversible reactions typically will have these arrows that head in both directions. So that is basically what a reversible reaction is. It has a forward direction that goes from reactants to products. And at some point when you build up enough products, those guys in these type of reactions will actually start reacting with each other. And that will force the reaction to head back the other way, going from products to reactants, which is known as the reverse direction. And when we talk about something reaching equilibrium, as we might talk about last time, it does not mean that you have the same amount of everybody on each side of the arrow. What it means is the rate of the forward reaction will equal the rate of the reverse reaction. So just as quick as it goes to the right, those guys will sort of recombine and go back to the left just as fast. The result of that is you pretty much will lock everybody into place in terms of their concentration, wherever they may be at that point. And they really won't change concentration, or they really won't change pressure if you're dealing with pressures, because they're kind of going back and forth at exactly the same rate. Again, doesn't mean that they have the same amount on both sides. There is a relationship that you can write for an equilibrium, which is known as equilibrium constant, and that is capital K. And the equilibrium constant is calculated by taking the concentration of your products divided by the concentration of your reactants. And that's what the little brackets mean. Brackets mean concentration. And the most common unit of concentration is molarity, which is moles per liter. So we also do take the coefficients into account as well. So if we were to write the equilibrium expression for this guy, this reaction here, it would be K is equal to our products, which would be the concentration of C, and we would square it because of the coefficient that is there, divided by the concentration of A, which would also get a square because of the coefficient that is there, times the concentration of B. Coefficient here is 1, so we don't have to obviously square it or anything like that. It's basically to the first power. This relationship here is a constant value, and it will always, no matter in a reaction like this, no matter if you started with a lot more reactants in one experiment or a lot less reactants in another, you started with some reactants or products in the experiment, it will always come to rest at the same proportion of products to reactants, which is our equilibrium constant here. And the only thing that affects the value of the equilibrium constant is temperature. If you do change the temperature, it will change the value of it. But if you keep the temperature constant, it will basically stay the same, the value of K. There are a couple of things that we do not include in it. If it is a solid or a liquid, it is not included in the equilibrium expression. That basically means you have aqueous stuff or gas that is included. So those are really the only two things that you include in there. It's anything that has an aqueous symbol or anything that has a gas symbol are the two things that you do include. Any questions on any of that there? Okay, so let's continue on talking about that. What does the value sort of tell us? One of the nice things about K is it is actually one of the few things here in chemistry that doesn't have units. It really is just a number, and the number basically tells us one of two things. If you have a large value of K, it will tell you that when that thing reaches equilibrium, you should mainly expect to see products have been formed. If you have a small value of K, what that means is when it reaches equilibrium, you should mainly expect reactants to be formed in that reaction. What is considered a large value? It is 1 is considered a large value. So anything 1 and above, if you're given a K value for, you would assume that you would have products at equilibrium. Anything less than 1, it would be the opposite. You would expect to have reactants at equilibrium. And again, it's just mathematically speaking, a large number is achieved by having a large top number and a small bottom number when you divide, and vice versa. A small number means you have a larger bottom number and a smaller top number when you divide two numbers. All right, so I think we got to here. And again, here are greater than 1, large value, smaller than 1, a more reactants when it reaches equilibrium. Now, if you do happen to hit a K value around 1, that means you pretty much got equal amounts, and it can happen. But in most cases, you'll kind of be one way or the other over 1, but it is possible to get close to it. To calculate the equilibrium constant, you do need to obviously have equilibrium concentrations given to you to put them in there. So if we look at this reaction here, this is hydrogen plus oxygen makes some water gas there or steam, has a K value of 2.9 times 10 to the 82. That is a giant number. And that giant number means even though this is a reversible reaction, pretty much we would expect definitely products to be there at equilibrium. And with a value that large, even though it is reversible, it is essentially a one-way street here. Almost 100% of everything's going that way. But even in a situation like this, where you have such an incredibly large value of K, and it almost is 100% all going towards the product side, it is still a reversible reaction, which means even if it's a super, super small amount, there is some of it coming back the other way. But in this case, it's going to be very, very little coming back the other way because of the large value that we do see for K. Any questions on that there? All right, so as I mentioned before, big value to the product. Equilibrium lies to the right is what is sometimes referred to. To the right of an equation is the product side. If we have a small value K, equilibrium lies to the left, which is the reactant side. And again, if we do have kind of a value of 1, we're kind of very close to having equal amounts. Again, the only thing that affects the value of K is temperature. So if you do happen to change the temperature, you will have a different value of K. But if you did like 30 reactions and you just did different amounts and you kept the temperature same and you calculated K every time, it should come out pretty much equal every single time that you calculate. All right, so why don't you try one here? Why don't you calculate K based on this reaction and the values given to you? So calculate the value of K, see what you come up with. Okay, let's take a look. So the first thing we want to start with is, and we'll go with this, the gas here, is to write the equilibrium expression here. So our K would be our products. And we would need to square it because of the coefficient that is there. We would divide it by the concentration of A2 and the concentration of B2. Since they gave us the equilibrium concentrations of each of these guys, we could stick it into this expression, and that would give us K that is 0.5 squared divided by our A2 equilibrium, which is 0.25, and 0.25 for this guy as well. That gives us 0.5 squared divided by 0.25 and divided by 0.25 gives us a value of 4 for our equilibrium constant. First off, any questions on the calculation? Would we expect mainly reactants or products in this case? We would expect products. This is considered a large value of K, which means the equilibrium should lie to the right, which means we would expect more products should be formed there when it reaches equilibrium. Any questions on any of that there? Yes, sir. That is, so that's what you use for the exponent. So in general, if you had an equation like this, whatever those sort of coefficients are, they become like the exponents when you put it into this. So they go up on top for each of these guys. So obviously, if the coefficient is 1, you don't, it's just basically to the first power. So you don't have to really write it or anything like that. Yeah. Other questions? Okay. So there we go. That's good. They agree with us. All right. So the next thing we're going to talk about in terms of equilibrium reactions or these reversible reactions is an idea that was known as Chatleir's principle. And basically in this situation, what we have is we have a system that is at equilibrium and is perfectly happy, is going back and forth at the same rate. And then we do something to it. We add some type of stress to it. And basically what happens is when you add the stress, you pretty much mess up the equilibrium. And what that means is, you know, when we are at equilibrium, that rate of the forward direction will equal the rate of the reverse direction. So when we do some type of stress to it, it really messes it up. And because it is a reversible reaction, even though you sort of messed up the equilibrium, it's going to want to fix itself and it's going to want to try to get itself back to an equilibrium state. And there's really kind of 3 things that could happen to try to get it back to its equilibrium state. It can do what people refer to as shifting to the right, which basically means make more products. It could pretty much do the opposite, which is shift to the left, which means you would need to make more reactants. And the third possibility is actually one where pretty much nothing's going to happen. Even though you did something to it, there's going to be like no change that will occur. So those are really the 3 sort of options that you have here in a Chatleir's principle problem. It's either going to go to the right, it's going to go to the left, or there will be no change that will happen. But whatever it does, it goes to the right or it goes to the left. What's going to happen is after you added the stress, that reaction will once again find itself back at equilibrium. So like number 1 and number 2. So we're a nice equilibrium reaction. You screw it up, it fixes itself by making more reactants or products. It returns itself to that equilibrium sort of change. So what are some stresses that we could do to a system? Here are some stresses that we could do. We could do something with the concentration, which basically means we can either add or remove, is pretty much what you could do to that. We could also change the temperature, which also means you can pretty much increase the temperature or decrease the temperature. It's basically your two options there. You can change the pressure. Pressure and volume really go kind of together. And this is a lot of times dealing with a gas sort of equilibrium. And you basically do the same thing. You can increase it or you can decrease it. So obviously those are your two options for there. So we're going to talk about each of these things and sort of what happens, if you add more concentration, remove, or increase or decrease the temperature. So let us start with then concentration and sort of see what happens if we sort of play with the concentration. So looking at concentration here, again, pretty much two things you could do, which is add more. And that means you could add more reactants, you could add more products. And when you add, what happens is it will shift away from the side you added it to. So if you add more reactants, it will cause the reaction to shift to the right, away from the reactant side. If you add more products, it will cause it to shift to the left, away from the product side. If you're going to add more, it's pretty simple. Usually you just like go to the shelf and grab the bottle and you add more into your beaker. That's a pretty simple way of doing it. You just add more of whatever's there. The other thing that could happen is you can remove. And again, you can remove some reactants, you can move some products. When you remove, it will actually shift towards the side you removed it from. So when we're talking about sides, we are talking about, obviously, there's the reactant side and the product side of the equation. In the actual beaker, the test tube, there's no sides. There's no like, I'm on the left-hand side of the beaker, you're on the right-hand side of the beaker. But when we talk about sort of going to the left or going to the right, what we're referring to is the actual balance equation. And again, if we're going to the right, that means we should expect more products going that way. And if we go to the left, we should expect more reactants. So to illustrate this sort of idea here, let's take a look. By the way, how can we remove something from like a beaker that's all solution? Can we just reach in and grab it? Yeah, that's not a, no, you shouldn't really reach in and grab it, right? Because that's not a great idea. And there's no solid there to grab. So one thing that you could do to remove something is you could actually add something to the reaction that actually will make a solid. And so you could add some other reagent to it that will make a solid. And that's important because essentially a solid is not part of the equilibrium. So if you remember, we do not include solids in the equilibrium expression. So if you add something, so for example, if you had like some chloride ions floating around, you could add some silver to them. And that silver and that chloride would come together and make silver chloride, which is a white solid. And that would essentially be like reaching in and taking the chloride out of the solution, and it would no longer participate in the equilibrium because it's a solid. Another way that you can sort of remove something, especially if there are basically H plus or hydroxide in the reaction, is you could add either acid or base to it. And because H plus and hydroxide like to come together to make water, which is a pure liquid, So you could actually make water, which is something you can't really see. Usually when you make water, you can't go, oh, I just made water. It just looks like the same as what you had before. But that's a very common way that we remove something like hydroxide from a reaction, or H plus, or from a reaction, is either add acid or base, and you will make water. Water, which is a pure liquid, also not included in the equilibrium constant because it is a pure liquid. So again, that would be like removing. So those are the two common ways you could kind of remove something from a solution, make a solid by adding something else that's not there in the reaction, or adding something to really form water, which is typically an acid or base you would do in that particular case. So if we look at this here, let's say we had a system that was at equilibrium. And we'll say we are at equilibrium here. We'll call this guy over here the reactant side, this guy the product side. And let's just say we had somebody jump on here to the product side. What's going to happen is clearly we're going to mess up this equilibrium, right? That's advanced stick figures. There's faces on that one there. So we clearly kind of mess up the equilibrium by adding more products in this case. To fix it, do we need to put more people on the right-hand side or the left-hand side? We would have to fix it by going away from the side we added and put more people over there on the left-hand side. And if we did, we once again can come back to equilibrium here. And we're back to equilibrium. So this is sort of what happens when we add more products. Obviously, if we did the same thing to the reactant side would come down. So we would have to put more people back over on the other side to the product side to do that. Let's take a look at what happens if we ended up removing some people. So we'll start at our equilibrium position once again. And again, this guy's our reactant, this guy's our product. Now, instead of putting somebody on the product side, we're going to say this guy's just going to hop off. When he hops off, what's going to happen is we're going to get this deal, which obviously not a good day over there on that side of the teeter-totter. To fix this, we need to put more people now back on the right-hand side. So in this case, we're actually going to shift towards the side we removed it from. That's going to allow us to come back to equilibrium and make everybody happy once again here. And equilibrium once again achieved here. So this is sort of the idea that happens when we talk about, Le Chatelier's principle. Something is done to that equilibrium, it really messes it up, but the reaction tries to move in a way to counteract the messing up of the equilibrium, and in this case, one way or the other. Any questions on that there? So if I had, this reaction here, say 2A plus B goes to C. If I added more A, which way would it go? It would shift to the right. Again, we're adding A, which is right here. When we add, it goes away. AA is a good way to remember that, add away. So we're adding, we'll shift to the right. If I removed B, which way would it go? It would go to the left. Again, when I remove, B is over here. It's going to go towards the side I removed it from. If I added C, it would go. It would also go to the left here. Again, add away. So we're adding on the right-hand side of the arrow, going to cause the equilibrium to shift to the left. Any questions on any of those there? Okay, the next thing we're going to talk about in terms of Le Chatelier's principle is the idea of pressure and volume. And really, both of these guys are sort of tied together. as we'll talk about in the next chapter, when we talk about gases, pressure and volume are related to each other, basically opposites of each other, which means if the pressure increases, the volume will decrease. And that is because in a very small volume, if you've got gas molecules flying around in a very small area, they're going to have a lot of collisions. And it's really the collisions that occur which causes the pressure to increase. So in that very small area, a lot more collisions, we would expect the pressure to come up. And opposite is true if we drop the pressure when we have a much larger volume. So in a much larger volume, everybody has a lot more room to fly around in, which means it's going to take longer for collisions to occur. Because it takes longer for collisions to occur, we would expect the pressure to go down. So if we increase the pressure, which basically means we are decreasing the volume, the real change that's happening here is the pressure is going up, but we have a much smaller volume because of that. So if we wanted to counteract the pressure going up, would we need more gas molecules or less gas molecules in the smaller volume? Let's just say I put a lot more gas molecules in the small volume. Would the pressure continue to go up or would it come down? It would go up, right? A lot more gas molecules, a lot more collisions, pressures can go up. If I lower the number of gas molecules in that small volume, we should then see the pressure start to come back down. So if you increase the pressure, which decreases the volume, it will cause the equilibrium to shift to the side with the least number of gas molecules. Now, obviously, that is dependent on the equation you're looking at as to which side has the most gas molecules or the least. You could do that by simply adding up the coefficients on each side for anything that has a G next to it, right? Which means it's a gas. So you can just add up the total gas you got on the left and total ones you got on the right. Opposite is true here. If we lower the pressure, that means we have a bigger volume. So kind of the opposite here. The change that's happening is the pressure is decreasing. So we kind of want to bring the pressure back up. So we have a much larger volume. So we would need a lot more gas molecules in that bigger volume to get the number of collisions up and bring the pressure back up. So it would shift to the side with the most gas molecules. Personally, for me, because these two things are related to each other, I always think about it in terms of volume. So if you have a small volume, you need less gas molecules in that smaller volume. If you have a larger volume, you need more gas molecules. So I remember this relationship of how pressure and volume are related to each other. And again, I just sort of think about it in terms of volume. A smaller volume need less. Small, less, and larger volume, you need more gas molecules. So that's a good way to sort of think about it. Question on pressure or volume here. All right, the other sort of change that could occur or stress that you could do to a system at equilibrium is temperature. And temperature really is related to, really works the same way as concentration. So that's sort of the nice thing about temperature. Temperature works the same way as concentration. Which means if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. Obviously, increasing temperature would be like adding more, and decreasing the temperature would be like removing it. So what helps you decide sort of which way that is? It has to do with what type of reaction you are dealing with. Are you dealing with an endothermic reaction or a exothermic reaction? So if you are dealing with a exothermic reaction, as we've talked about, a couple of things will tell you that. Very commonly in Le Chatelier's principle is they lay up a delta H value and it is negative. Again, the sign doesn't really matter. It's just you see a negative delta H with the reaction, you know it's exothermic. What that means is energy is being given off. And what we think about in terms of exothermic is heat and energy is considered a product. Not 100% correct, but it is considered to be a product, which means if you have a exothermic reaction, you increase the temperature. Which way should it shift? It'd be like adding heat and energy, which means you add to the right, it should shift to the left, right? It should shift away from the side you added it to. And if you decrease the temperature in an exothermic reaction, that would be like removing this guy, which means it should come towards it, and we should see it shift to the right. Any questions on that one there? That also means if we have the opposite situation, an endothermic reaction, our delta H value will be a positive number here. And what we consider heat and temperature and energy as being a reactant in an endothermic reaction. It is a reactant, which means kind of the opposite. If you have an endothermic reaction and you increase the temperature, you are now increasing the reactant side, which means it should add to the reactant and shift towards the product side to the right, away from it. And if you decrease the temperature, that would be like removing a reactant. Again, when you remove, it should come towards it, and it should head towards that product side, or the reactant side. So it's really important in these type of situations to understand, is the reaction exothermic or endothermic? I would say probably a very common way is they just give you the delta H value. And again, the number is not really important. It's the actual sign that you see. Sometimes they will write like heat into the reaction. So based on which side it's on, will tell you it's exothermic or endothermic. Or sometimes they'll actually just put an energy value on one side of the equation or the other. And again, based on which side it's on, should tell you if it's exothermic or endothermic. Any questions on temperature here? One last thing, which really doesn't affect the equilibrium, but sometimes talked about with Le Chatelier's principle, is the idea of adding a catalyst. And I think we might have talked about catalyst, but just to remind you, in case we didn't, catalyst is not a reactant, and it's not a product, and it does not get used up in a reaction. It is really there to facilitate one thing. It's usually there to facilitate speeding up the chemical reaction. And really how it does that is, as we talked about, every reaction has this activation energy between the reactants and the products. Again, it's that hill that the reactants has to climb to get to the products. By introducing a catalyst, it finds some alternative pathway. And what it essentially will do is lower that activation energy. And the result of that is, because the energy hill is much smaller, it is easier. And there's a lot more guys that have enough energy to get up and over to the other side. And what that does is basically usually speed up the chemical reaction in this case. When you add a catalyst, it just gets there faster. There's actually no change occurs. So that is one way you could actually get a no change situation, is if you add a catalyst. Another common thing that is mentioned is if you add a noble gas, for example, helium, neon, or something like that, to a gas mixture, because those things are chemically inert, they won't interact or anything with the other gases that are in there, and it will cause a no change. The third way you could get a no change is what we were talking about a second ago, which is this guy here, pressure and volume. You end up with the same number of gas molecules on each side. So there is no more or less. They got the same amount of gas molecules on each side. That would also be a situation where you could end up with a no change. Any questions on that there? All right, so let's take a look at a reaction here. I'm going to make up. Let's do 3A, that's a gas, plus B goes to 6C, delta H positive 325 kilojoules. All right, for this reaction here, tell me, will it shift to the right, shift to the left, or will there be no change if we add more C, we remove A, we decrease the volume, we increase the temperature, we decrease the pressure. Let's also do, let's see here, we add more B. And let's see, let us do those guys right there for now. That's good. All right, so for this reaction, if we do all these things to it individually, what will happen each time we do each of those things? So we are going to start with, first off, why don't we look at what we got going on here? So we got this equation, and we do have a delta H value given to us, which is basically our energy value. Is this reaction endothermic or exothermic? It is endothermic because only of the positives, all you're really concerned about there. That means when we think about heat and energy, should it be a reactant or a product? It should be a reactant. So it would be on our reactant side if we want to kind of put it in there. All right, so I think we got everything we need here to kind of roll through these. We're going to add more C, which means it should shift. It should shift to the left. Here we are adding on the right-hand side. So it's going to shift away from the side we added it to. If we remove B, I'm sorry, if we remove A, what will we end up with? Shifting to? It will also shift to the left. Once again, we always shift towards the side we're removing it from. So it's a, the idea here is if we added more C, for example, we have more products. More products means that they're going to be able to react with each other faster. And that's going to basically kick off the reaction, the reverse reaction going to the left. When we remove A, which is a reactant, it's like A is like depleted, right? So we kind of have to fill the hole back up. So we need to go towards it to kind of fill the hole back up. So that's why, again, it shifts towards the side we remove it from. If I decrease the volume, which way we're going to go? So if I decrease the volume, that means really the pressure should go up, right? And that's because we have a smaller volume. So do I want more or less gas molecules in the smaller volume? Want less gas molecules. So we do have to look at the equation here to see which side has the less. And it is as simple as each of these guys are gases, and there's a 3 here and a 1 here. That is 4 gas molecules there on the left-hand side. Right-hand side, that is gas, and there are 6 on the right-hand side. So since we do want it to go to less gas molecules in this particular reaction, that would mean going to our left-hand side, which has 4. Any questions on that one there? If I increase the temperature, it should go to the right. So it works the same way as concentration. Since we determined that this is endothermic, we have our heat and energy on the left-hand side. So we're adding to the left, which is going to make everybody go to the right. Really for the same reason, you're adding energy, going to give all those reactants now enough energy to start reacting, going to kick off the forward reaction, which is why it goes there to the right-hand side. If I decrease the pressure, that means what happens to the volume? Volume goes up, which means that's the way we want to think about it. Bigger volume needs more gas molecules. So in this particular case, that would be to the right. And lastly here, if we added more B, it should go should go to the right as well. Any questions on any of those there? All right. So just going through some of the examples, I think that were in the handout here. We have this reaction, and if we added more CO, once again, adding more of our reactants, going to allow these guys to really start reacting a lot quicker and going to cause that equilibrium again to shift to the right in this case, going to really cause that forward reaction to occur. Remember, we talked a little bit about, what kind of increases the rate of reaction, and that is, the amount of guys that are there. So more guys there, they don't have to go find each other. It's going to really help the reaction occur. Obviously, increase in temperature gives everybody a lot more energy to get up and over the hill to the other side as well. Obviously, here, if we increase CO2, the opposite would occur. We have a lot more CO2, which means they could start really breaking down and heading in the opposite direction there as well. If we removed water in this case, it would come towards the product side. Again, you could think of this as like decreasing the amount. So almost like you made a hole. So you need to come towards that side and kind of fill it back up as you depleted it on that side. And then in this case here, our temperature, once again, we see our delta H given to us. And really the only thing we're concerned with is the positive value. And that is an endothermic deal, which means really our heat is over here. So if we increase the temperature, it'd be like increasing our reactants. Once again, increasing that going to cause the reaction to shift away from it, as we talked about there. And again, as I mentioned, pretty much gives these guys way enough energy, or a lot more of them, enough energy to get up and over to the product side, allowing that forward reaction really to dominate at that point. Obviously, in this case, this is an exothermic reaction, as we see from our negative, which means, again, we can think of heat as being a product, which the opposite is true here, as we just saw. We will now increase our product side, really giving our products enough energy to go the other way, because as it goes in this direction, our products are like our reactants, kind of what's starting to break back down, and we would get it to shift away. In this case here, we would decrease the pressure, increasing the pressure, which means that our volume would decrease. So again, we want to go to the side with the least number of gas molecules, as we see here, which would shift to the right. And opposite is true. If we decrease the pressure, we now need a lot more gas molecules to fill that hole, because the volume should increase. So bigger volume, more gas molecules when you do it. Any question on Le Chatelier's principle? Here's just a table of basically what we talked about and sort of the changes that occur. Question on equilibrium, Le Chatelier's principle. For us, probably the Le Chatelier's principle is the stuff you should focus in on, I would think, for equilibrium, and how to write an equilibrium expression, and what it means in terms of, if it's a large number or a small number. Question? Yeah. You mean in the react for the delta H value or something like that? Yeah, they will. They will, I think. So really, like I said, there's kind of like two ways it's either expressed to you. A lot of times, like we saw here, they'll just kind of give you that delta H value at the end of the reaction. And again, if they don't put a negative sign, you should safely assume it's a positive number. If it's negative, they definitely would put the negative in there. The other way is, like I said, they will just kind of write like a number in on one side, like plus, 30 kilojoules of energy or something like that. And then you can see it's on the product side, you'll know it's exothermic. And obviously, if you had one where they wrote it in, like over here, 30 kilojoules of energy plus something, if you see it on the reactant side, you'll know it's endothermic. So yeah, those are the two sort of common ways it's sort of put in there. The third way would be not a number, but just say heat generically or energy on one side or the other is another way to do that. Other questions? All right, that wraps up chapter 6 here. So give me a second and we'll go on to 7 liquids and solids in here. So we're going to start with gases. So there are certain substances that do exist as gases under normal conditions. And what substances those are, when we talk about sort of normal conditions, that is kind of room temperature. So that's like 25 degrees Celsius, 1 atm, which is a pressure. And under sort of normal conditions, ionic compounds really do not exist as gases. And that's really because they're held together by really strong electrostatic attraction, that positive negative attraction. That's a really strong attraction. And under normal conditions, it really will never sort of go into the gas phase. You could heat it with a lot of energy. What it will typically do before it would go into the gas phase is it will kind of just start to melt. So I don't know if maybe you did an experiment early on or something. Sometimes they do it with solutions, but you take like a salt solution, sodium chloride solution, you could evaporate off the water will evaporate off. And what you're left with is basically crystals of salt that's left over at that point. And you could heat that, continuously heat that salt. And really what will happen is it'll just really start to melt. It just takes too much energy to try to overcome the positive charged ion and the negative charged ion to get them away from each other to go into the gas phase. Now, covalent molecules or molecular compounds, they are very different than that. They come as gases, some of them just naturally the way they come, like carbon monoxide, carbon dioxide, hydrogen chloride, ammonia, and methane. But a vast majority of molecular compounds do come together or do come naturally sort of as liquids or solids at room temperature. The main difference between sort of a ionic compound and a molecular compound, again, a reminder, ionic compound is no sharing of electrons, right? Ions. And a molecular compound is covalent bonded stuff where we do have sharing of electrons. The major difference is you can much easier convert a molecular compound into a gas than you can an ionic compound. The most common example of that would be water. Water, right, normally comes as a liquid. Water is held together by what is known as hydrogen bonding between the positive side of hydrogen there and water and the negative side, the oxygen and water. They do what is known as hydrogen bonding. And that hydrogen bonding is what is referred to as an intermolecular force. It is much, much weaker than the bond that holds an ionic compound together, which is an intramolecular force. So when you go to heat something like water, what ends up happening, because this force is much weaker, you're much easier to break this bond between the two water molecules and allow those guys basically to go off into the gas phase. And that's very different than when you got a bunch of these sodium and chloride ions stacked in there together. You know, they're held together by very, very strong electrostatic attraction. And again, you could heat that, but it's not enough energy to really liberate those guys from each other. So it doesn't really happen in the case of an ionic compound. So the stronger the attractive forces between molecules or atoms, the less likely that it will exist as a gas under normal conditions. And again, that attraction between ions is pretty much one of the strongest attractions you could have. And that's why we don't see ionic compounds really as gases. But molecular compounds, you can obviously very easily kind of convert them into gases. Some substances that are normally found as gases under normal conditions, we have our diatomic molecules or our elements: hydrogen, nitrogen, oxygen, fluorine, and chlorine. Also ozone, which is O3, is also a gas. And then not to be confused or forgotten about are noble gases, which is group 8 on the periodic table. They are monoatomic gases, which means they come as one. And that's our helium, our neon, our argon, our krypton, our xenon, all the ons there are gases. So under normal conditions, if we look at sort of the periodic table, it's pretty much all this side here that's going to come as, along with our hydrogen, which is also a non-metal. will come as gases under normal conditions. So this is a good time to talk about the difference between two words that sometimes are used interchangeable, but there is sort of a difference between them. A gas is a substance that under normal conditions will be found in the gas state. And a vapor is a gas form of any substance that is normally found as a liquid or a solid under normal conditions. So water is a prime example of that. And that's why yeah. So, if you're asking, when something becomes sort of a vapor, it has to do with really the forces that hold those molecules together with each other. So, for example, water molecules, as I drew on the last page, are held together by hydrogen bonding here. And in the case of water, you need to get to approximately 100 degrees Celsius, right? Which is the normal boiling point for that particular substance there to turn into the gas phase. So different substances are held together by different sort of strengths of forces. And the stronger the force, the higher the boiling point would be. The lower the sort of force, the lower the boiling point. So for example, methane, which is this guy, CH4, stuff that comes out of your thing there when you light a Bunsen burner, your gas valve. It's held together with methane, other methane molecules by what is known as dispersion forces. And dispersion forces are super weak forces, which means you basically just sneeze at it or look at it and they're going to break apart. And that's why pretty much something like methane is found as a gas under normal conditions, because it's not held together very strong at all. So it finds itself as a gas under normal conditions. You don't even have to kind of convert it into a gas. It will just be a gas. While water has a relatively strong hydrogen bonding force that holds it together, which is why it's normally found as a liquid, but it's not a super strong that you couldn't apply enough energy to break it apart and convert it into a gas. And when things convert into a gas, again, it is that normal boiling point where that pretty much happens. And things that are held together strongly have very high boiling points, and things that are held together weakly have much lower boiling points. One way that we do measure pressure is the use of a barometer. And a barometer kind of looks like that picture I just put up there. But years ago, barometers, although nowadays I don't think there's too many, maybe, I don't know, I haven't been in your guys' lab in a while, but years ago, they used to be made out of mercury, and they used to have a tube in it. And basically what would happen is the atmospheric pressure would press down on the pool of mercury, and the mercury would rise in the tube, hence the saying mercury rising. And you would take a reading off of it, and it was invented by a guy named Torricelli here. And we take some common units of atmospheric pressure. 1 atm is a very common unit of pressure. 1 torr, which is named after this guy, is equal to 1 mmHg. mm is millimeters, hg is mercury, because that's what barometers used to be made out of. And basically on this tube would be a ruler, and you would read the ruler as inches, centimeters, or millimeters of mercury, and that's where that comes from. 1 torr is the same as 1 millimeter of mercury. And this is a really important relationship between the different pressures, which is 1 atmosphere is equal to 760 torr, and 760 millimeters of mercury. That 760 number is an important one. It is your conversion factor. If you have atmospheres and you want either torr or millimeters of mercury, you need to multiply by 760. Gives you torr or millimeters of mercury, which is kind of the same thing. And if you are starting with torr or millimeters of mercury and you want atmospheres, you're going to divide by 760. And that will give you atmospheres. So 760 is sort of an important little conversion number, allows you to go between the different units. Any questions on that? There obviously are other units of pressure like PSI, pounds per square inch, a bar, Pascals and kilopascals is used a lot in some sciences like physics. But here we use these three are kind of the biggest three that we use: atmospheres, millimeters, mercury, and torr, sort of the big three that we kind of use here in chemistry. Any questions on any of that? All right, we will lay it up there, I think.